P99 latency jumped from 45 ms to 3.2s, and order completion dropped to 72%, all because a chaos experiments probe missed the real failure. Here's exactly why. Welcome to the CodeForge. Before we dig into that production issue, let's cover chaos engineering basics. Chaos engineering is a scientific method for resilience. You start by defining a steady-state hypothesis, a measurable metric like P99 latency under 200 ms. Then you inject a fault, monitor the system, and abort if the hypothesis is violated. The goal is to find weaknesses before they hit users. The steady-state hypothesis is a contract on system outputs, not infrastructure. You're asserting that checkout completes within 300 ms for 99% of requests, not that the database stays up. Calibrate your threshold from real production data. Use the 7-day peak P99 times 1.5. Here's a Litmus ChaosEngine manifest that defines both the fault injection and the steady-state probes. The first probe checks the HTTP endpoint, but the real hypothesis is the Prometheus probe checking P99 latency. Blast radius monitoring requires 3 layers: infrastructure, service, and business. Without traces, you see a metric spike but can't trace the propagation path. Use OpenTelemetry to correlate fault events with traces, and always monitor business metrics like order completion rate. These Prometheus alerting rules fire during a chaos experiment. They detect retry storms, database connection pool exhaustion, and business impact. Note the experiment context label. It's used to route alerts to the watchdog service. The most dangerous moment is the gap between something is wrong and someone pushed abort. You need 2 layers, probe-based abort inside Litmus and an external watchdog in a separate availability zone. The watchdog subscribes to Alertmanager webhooks and aborts the experiment if a business impact alert fires. Here's the external watchdog service. It listens for Alertmanager webhooks and aborts the Litmus experiment when a severity page alert fires. It also captures a Grafana snapshot before aborting, preserving the system state for post-mortem. Running a chaos experiment without observability is like flying without instruments. You need Prometheus for red metrics, OpenTelemetry for distributed traces, and structured logs with an experimented field. Annotate your Grafana dashboards with fault start and end times so every chart is self-documenting. Always run your first 3 experiments in a production mirror environment. Once validated, graduate to a canary production experiment with a tiny blast radius. Ensure you have 5 graduation criteria, including a human-readable kill switch that any engineer can use to stop all experiments. Every chaos experiment starts with a bet. Write down your hypothesis with concrete numbers: P99 latency under 200 ms, error rate below 0.1%. Pull baseline metrics from the last 72 hours of real traffic. The gap between what you predicted and what happened is your engineering debt. Here's a Java record that formalizes an experiment hypothesis. It includes the expected P99 latency, max error rate, and a validate method that checks actual metrics against the hypothesis. Paper experiments fail because they don't account for the cognitive load of a real incident. Schedule a game day, pick a Friday afternoon, terminate a database primary, and watch what actually happens. The first game day is chaos, but by the 3rd, you're catching regressions before they hit customers. This Java code outlines a game day drill with 4 phases: pre-game, attack, observe, and retrospective. The phases are sealed and each has specific parameters. This is the same issue we highlighted at the start. Here's exactly why that happened. The Litmus experiment hogged CPU on 50% of checkout pods. Those pods became slow, causing upstream services to retry aggressively. The retries exhausted the shared database connection pool. 98 out of 100 connections were in use. The healthy pods couldn't get a connection, so order completion dropped to 72%. The probe only monitored the service endpoint, not the database pool. The fix involved 4 changes. First, add a database connection pool utilization probe to the Litmus experiment with a threshold below 80%. Second, implement an external watchdog service in a separate AZ. Third, Set Alertmanager routing to suppress primary on-call during experiments using a chaos mode label. Fourth, reduce upstream retry count to 1 to prevent retry storms. The probe only checked the checkout service health endpoint. It didn't monitor downstream dependencies like the database connection pool. When retries exhausted the pool, the probe still saw HTTP 200, so the abort came too late. Always monitor downstream dependencies. Setting SSH thresholds by intuition instead of data leads to false aborts. If your real P99 is already 250 ms on a quiet day, a 300 ms threshold gives only 50 ms of headroom. Calibrate from 7-day production data. Set the threshold to 1.5x the observed peak P99. If your chaos experiment kills Prometheus or the cluster it runs in, probe-based abort won't fire. You need an external watchdog in a separate availability zone with its own monitoring stack. This is the safety net when your safety net fails. The ChaosEngine manifest shown uses Litmus EO/v1 alpha 1, which was deprecated in Litmus 3. For Litmus 3x+, use Litmus EO/v1 beta 1 and the new Chaos Experiment CRD. The probe field structure also changed. HTTP probe/inputs is now HTTP probe with a URL field directly. Always check the Litmus release notes before applying examples. The article mentions encoding SSH as a Prometheus recording rule, but doesn't show it. This snippet creates a recording rule that computes the 7-day baseline P99 latency, which can be used to calibrate SSH thresholds before an experiment. The article mentions suppressing on-call during planned experiments, but doesn't detail the routing configuration. Without proper Alertmanager routing, experiment alerts can page the on-call team, causing unnecessary rollbacks. Use a chaos mode label on all experiment-related alerts and route them to a separate receiver that does not page. When a chaos experiment causes unexpected impact, start by checking the probe configuration. Ensure probe mode is continuous. Verify Prometheus connectivity. Use Jaeger to find traces crossing dependency boundaries during the fault window. Check circuit breaker state on the caller service. Let's run through some common interview questions. What is a steady-state hypothesis? A measurable, bounded output metric that defines normal system behavior. Why 2 abort layers? Probe-based abort fails if experiment breaks monitoring. External watchdog in separate AZ provides fail-safe. How to calibrate SSH thresholds? Measure 7-day baseline P99, set threshold to 1.5x observed peak. And a few frequently asked questions. What is blast radius? How far a failure spreads through the system? When should I run chaos experiments? When system has dependencies and you ship frequently? What if experiment breaks monitoring? External watchdog in separate AZ with independent monitoring. To recap, chaos engineering is a disciplined practice. Always define a steady-state hypothesis with measurable output metrics. Monitor blast radius at 3 layers. Use 2 abort layers, probe-based and external watchdog, and calibrate your thresholds from real production data. Ready to go deeper? Up next, Introduction to Ansible, then Ansible Playbooks Explained, then Ansible Roles and Best Practices. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.